I'll send a link. I'll put a link on Canvas. I'm not sure, but if you just Google stellar evolution, it's there. You'll see something that matches up. Oh, come on. Technical difficulties. Well, it's up there. Okay, well I'll just try to snag it from there. Oh my gosh, there's like nothing on my thing now. It looks like, this is the one I want. Oh, maybe. Okay.
So I have this silly. I'm pretty sure it's not mine. I'm like 99% sure it's.
I try not to listen to conversations, but yes.
You know who Madison? Madeline Ryan. I think she was at my house a couple nights ago with my sister. She was like not feeling good, so I guess she like.
I found it, everybody. So we've been talking about HR diagrams. We've been talking about what does the H and R stand for? Does anybody remember? Two names. Hirschsprung and Russell, HR diagrams. So the thing about HR diagrams, and you might want to be able to draw one on your test next Friday. Yeah, you're going to want an HR diagram. You're going to want to label the axes. Of course, we have temperature from hot to cold. We can also do O, B, A, F, G, K, M, right? Stellar types. And then we have luminosity along the, what's luminosity?
Brightness.
Brightness, exactly. Energy. Energy is pumping out brightness. So it goes something like this. I've got a couple of clusters of stars here. Now, they aren't the dots, but pretend that this black line represents like stars are all like this, and then they go like that. So what's this region up here in the upper right-hand corner, kind of?
Supergiants.
Giants, supergiants, perfect. So this is one cluster of stars, and this is another cluster of stars. I don't know if my pen marks. Let's see. It's kind of having issues. If I put the letter A here, nope. Okay, but picture this is A and this is B. So which one is older, A or B, set of stars? B. Why is B an older set of stars? Because the turnoff point is lower down. Perfect. Yep, that's it. Very good. So this actually kind of see the little arrow here, and we have some stops along the way, A to B to C to D. Okay. So this actually, what's happening in the core of the star when it leaves the main sequence? Or what has stopped happening? It ran out of hydrogen to fuse in its core, exactly. So we kind of have some interesting sort of kind of back and forth up here in the giant or supergiant areas, exactly. Yep, and I'm not going to get into the nitty gritty, the details. I'm not going to. I don't have to. So we're going to talk, I'm going to put it on the board, the mass is kind of the thing about it. So low mass stars are, on the sheet I gave you, down here there's a box that says something like less than 8m. And that m right there is the mass of our sun. So less than 8 times the mass of our sun. That's a low mass star. Okay? Now even lower than that, actually, and kind of falls off, people forget about these guys. I'm going to kind of do what's a very low mass star. If I had the main sequence here, what are these guys down here? Red dwarfs, very good. Very, very low mass. Those are red dwarfs. And actually, for purposes of today, they fall off the radar. These guys are between 0.08 and 0.4 times the mass of our sun. Okay, cool. So, including our sun, so is our sun less than 8 times the mass of our sun? Yes. Does that make sense? So our sun is going to do this. This is a low mass star. See the different colors? The different colors are different, we call different fusing areas. So if I put our sun, oh my gosh, our sun, there it is. I put our sun over there, you told me that when it leaves the main sequence, what stars like our sun, bless you, have done is basically all the hydrogen in their core anyway has been converted to helium. And what our sun's going to do, in the video talked about this, is actually the core is going to squeeze in on itself. It's going to increase the temperature and the pressure in the core. So now that helium that was just hanging out because it was left over from hydrogen fusing to form it, it begins to fuse to begin to form carbon. Okay? So our sun is going to do that. That's the one last thing, and I think the video talked about it's got one last leg to stand on. Okay, so that's what's going to happen. And so we kind of end up with this the most complex, or the most complex elements in the center, and then least complex, least complex, least complex. It kind of looks like an onion. So we have carbon and oxygen. If I had a periodic table of elements, you would see then that helium, of course, is less complicated than that, and hydrogen is less complicated than that. So this is kind of the way all stars are going to do this. So like on the sheet I gave you, okay, we're talking this down here. These are low mass stars, and I put a little box there. So I have a few more things to talk about low mass stars. So what else about low mass stars? This actually kind of shows a star about the size of our mass leaving the main sequence. When I say leaving the main sequence on the HR diagram, it goes off of that diagonal part. It comes up here in the giant region. Like we saw before, it kind of wiggles back and forth. Okay, and then actually at some time it's kind of done. It's done being as complicated as it's going to be. It's got carbon in its core. And then there's this important thing. It's also on your sheet called a planetary nebula. And that is actually when the star has gone into retirement, ready to kind of just give off its gases that it's been kind of collecting. Gravity lets go of it, and it makes this kind of pretty cocoon shape around it. So in doing all of that, actually, nebula can actually be places where more stars can be born from that material. Down here, this is part of this graph, and it just kind of shows you, in here, the little pink, it says inert helium. Now the word inert just means it's just hanging out, just dormant. The next one I'm going to show you, it says actually helium is fusing. The pink says helium fusion. And that's going to give us, and I have a little slide to kind of show you how that works, but helium is going to give us carbon and oxygen. So that's kind of what we have for low mass stars. You know, sometimes and we will talk about stars that blow up. Stars that blow up are going to be greater than 8 solar masses, 8 times the mass of our sun. They're going to blow up. And a lot of times people come into this course and they think, well, all stars blow up when they die. No, not all. Ours won't. Okay. So I've got some pictures of some planetary nebula. And just like other cosmic objects, other objects out there in outer space, they have proper names. Like this one is called the Ring Nebula, and this is in the constellation Lyra. Now the thing about a planetary nebula is if somebody says you're looking at one in the telescope, well, you should be thinking to yourself, that's a planetary nebula. I probably have I'll put my thing up here. What's this down here? What are these guys?
Red dwarf?
These are red dwarfs, these are white dwarfs, yep. These are white dwarfs. If somebody says I'm looking at a planetary nebula, it has nothing to do with planets. I think historically they kind of saw the little blob up there and thought, well, that's another planet. And it wasn't, because it's not orbiting our sun. But anyway, if you look at that, you should kind of be thinking, I bet there's a white dwarf. I'll put WD here for white dwarf. I'll put RD here for red dwarf. I bet there's a retired star there somewhere. I love that. The older I get, the word retirement is a pretty word. This is another planetary nebula. It's generally taking on kind of this butterfly shape. Okay, again, there's a central, I guess I should call it star, a retired star that no longer has nuclear fusion going on. That's why it's retired. Here's another one. Aren't they pretty? This one, the caption, if you read it, this is also a planetary nebula, and you can kind of see the different regions, the 3 different regions kind of. If you're an astrophysicist, those 3 different regions, you're like, oh, well, it did this then, it did that then, they're associated with different kind of stages of what that retired star is doing. These are planetary nebula. Very pretty. So this is kind of showing you maybe how do you get those butterfly planetary nebula. Okay, there is the retired star, and it's kind of, its stellar wind is blowing out the material on either side. All right, so HR diagram. Notice we have hot, cold stars. Main sequence is that diagonal we've been looking at. And you guys told me this is red giants up here, and we're kind of seeing how actually, so what's the temperature-wise, what's the difference between A and C? Which one's hotter? C is hotter, very good. It's hotter, and that actually we see it's on it, but it's retired. So it's kind of neat if you, it's poetic. Basically, it's just kind of giving off all of the energy it hasn't given off so far. So look at the sheet I gave you, and I don't think this is a term on your lecture notes. So now you kind of see, what's a white dwarf going to turn into? A black dwarf. I know. It's just gonna kind of lose its thermal energy over time. I know. I've heard, and there must be some truth in this, the idea of carbon, right? Carbon. So what are diamonds made of? So I've heard something like these white dwarfs, they might actually be a really kind of cool source for actually having elemental carbon, high pressure. I know, you're like, so this is a white dwarf. HR diagram, let's see. Now, so white dwarfs. So this, you guys told me that C is hotter than A, and you're right, but hopefully we kind of figure that over time, C, which is a white dwarf, is going to go down here and it's going to cool down, become low luminosity and cool off. White dwarfs are really cool, no pun intended. So the guy on the video, we said that white dwarfs, the guy on the video said if you were to go visit it, it's very dense. It's got, okay, because you figure gravity basically has been working on that object since it became a star in the first place. And gravity didn't stop. It sort of did with basically electrons bumping up with electrons. The electron degeneracy stopped it from squishing down any farther. So a white dwarf is very dense. And it's a little bit backwards in that the more massive the white dwarf, the smaller it is. Why would that be? If it has more mass, why is it small? The radius.
Contracted so far.
Mm-hmm. Yep, if it has more mass, it actually squishes down even more. It's so bizarre. Yeah. But again, it squishes down. We're going to be talking about this more about how matter can only squish so far. So you guys told me the other day that if I have atom A, this is the nucleus of atom A, this is the nucleus of atom B, of course I'm going to go ahead and make my electron cloud around it, and you squish those as much as you want, but those electrons are going to bump up against electrons, and it's going to stop. Because actually when we talk about when stars blow up, that is not the case, but this is the case with white dwarfs. They stop. Oh, here it is. If you were to take a teaspoon of a white dwarf, it would weigh 15 tons on Earth. Like, oh, goodness gracious. I know. So this is I had an Indian student one time, and I butchered this last name, but it's Chandrasekhar. It's what I call it, Chandrasekhar. So he is, I believe, an astrophysicist that actually said at some point, actually we call this electron degeneracy. Those electrons from those two atoms hold it up. At some point, honestly, you're going to have a situation where gravity is going to actually, and I'll take these are my electrons clouds, and I'll kind of slip here, then the electrons are going to not hold up the material. And he said white dwarfs, these WDs, okay, they can only be, if they get any more, I'll put this, WD needs to be less than 1.4 times the mass of our sun. If your white dwarf is any bigger than that, this happens. And when I went like this happens, something's gonna give. Yeah, it's an explosion. Yep. So that limit is called the Chandrasekhar limit. Sorry, Dr. Chandrasekhar, for butchering your name. So in talking about white dwarfs, we actually already saw this. This is the dog star, Sirius, which actually, if you find Orion one of these days, then it's kicking around. Well, it's not kicking its dog around. It's a companion dog. So the bright star in Canis Major is Sirius. And if we switch from visible to infrared, we can actually see it has a companion there. Isn't that adorable? So this is an active star, and this is a retired star, the white dwarf back there. Do most stars have companions? Okay. Now, so when I talk about low mass stars, what is the kind of the limit? Yeah, 8 masses of the sun, exactly. So the title of this next one is Deaths of Massive Stars. So let's see what we got here. So I think we're probably pretty good with, we just did all this in the previous part, and now we're going to do this up here, right? Roadmap. Deaths of massive stars. And we'll be kind of, I read them in my office recently, but we'll kind of read them together. This is in our Milky Way galaxy, and I don't see anything about deaths of stars. I think, oh yeah, there it is. Okay. So can you see this star here with this little ring of material around it? Okay. And then if you look down, you see a puddle of material. You look up, you see a puddle of material. Well, actually, it kind of goes out like it came in. Do you remember the protostars sometimes would have jets of material going out like this? Okay. And what you're looking at is a remnant of a massive star that blew up. We call the stuff that's ejected actually massive stars that blow up, we call a supernova. And then the stuff it leaves behind, we call it, like if you go to the material store and you buy little pieces, they call those remnants. Yeah. This is a supernova remnant. So you kind of see it as skirt material and kind of So that's a supernova remnant. So high mass stars then must be mass stars, and I'm going to actually split high mass stars into 2 endings coming up here. But high mass stars are greater than 8 solar masses. Yep. But they leave the main sequence and they join this giants/red giants area. Okay, and over here, by the way, if I'm pointing up here to red giants, what would you say? What is their temperature relative to even white dwarfs? Are they warm or cool? Cool. They're cooler. Yep, they're cooler. But what are they with regard to luminosity? They're high luminosity, cool. Yep, supergiants, red giants. So element-wise, C stands for what element? Carbon. N stands for nitrogen. Very good. O stands for oxygen. Perfect. So there is this cycle they call the CNO cycle, which if you're a star that is more than 8 solar masses, you're going to live your life pretty quickly on the main sequence, and honestly, you're just going to live your life quicker, just period. Okay. Live in the face of the fashion line, exactly. So there's some kind of cool things that within the star, it doesn't, one way to think about it is it doesn't, the nuclear fusion, I'll take my sun away because it's not a massive star, but the nuclear fusion going on in its core is more complicated. So that's how it can be so fast. So I'll just leave it kind of general like that. But this wheel kind of shows you how carbon, nitrogen, and oxygen kind of make it go fast. Make it go fast, fast, fast. So I actually added to this table. When I posted to Canvas, these PowerPoint slides, if you printed them out. I didn't have these 2 years. So I'm going to kind of walk you through what's happening in the core of a massive star. Do you remember with the low mass star, we end up like kind of like an onion? We're going to end up like an onion with a high mass star too. Okay, so a high mass star starts out on the main sequence doing this. A high mass star starts out on the main sequence just doing that. Notice it doesn't take very long though, and it has the same temperature requirement as our sun has. Then in its core, it will do what our sun is going to do. It will go ahead, a high mass star, the next stop in the core is to go ahead and begin taking the helium that it made by fusing hydrogen, and the basic product it's going to form, it's going to produce carbon. It's going to build up carbon, and that's where our star is going to stop. Notice, what would you say with regard to the temperature to fuse helium? It's higher, exactly. It takes it up a notch each time. So now our sun is not going to do this. It just can't. It's going to turn into a white dwarf. But more massive stars are it's going to go ahead and gravity's going to kick in. It's going to increase the pressure, increase the density in the core, so it can successfully fuse carbon. And one of the main things it's going to form is the element neon. What's the symbol for neon? Ne. Yep. Notice the temperature is hotter. The time is pretty short, 600 years. That's not very long. All right. Well, then it's going to take its neon, and one of the main things it's going to form is oxygen at a higher temperature. I'd say higher, only in a year's time. So one of the things, as we here on Earth try to kind of look at massive stars, thinking, now when is she going to blow, right? So we try to. So then it takes its oxygen to make silicon. Now, if you were to find silicon on the periodic table, if you were to look at silicon, silicon's a more complicated atom. It has more protons in its nucleus. That's what you get with fusion. Higher temperature, 6 months, oh my goodness. And then last but not least, we have silicon to forming the element iron. So what's the symbol for iron? It is Fe. You have to form iron. Very hot temperatures, high pressures. And how long does it last? Just like 24 hours. Those would be Earth days. Are you serious? Oh my gosh. And do you remember the video where the guy was in a foundry and he's made this big deal about iron? Iron is the most complicated element that a star can end up with in its core. Because it goes ahead and it runs out of silicon. It's just got a core of iron, and it wants to do what it did before. Increase the pressure, increase the temperature. The problem, I don't know if you're familiar with endothermic or exothermic, but the problem with trying to fuse iron is it doesn't release energy, it absorbs energy. So it's not happening, okay? It requires energy. So it's an abrupt stop. I'm going to talk more about that abrupt stop. But just know that the iron core, it can't do anything more. And it tries to do what it's been doing, but it doesn't work. Yes?
So after iron, there's no more fusion then?
After iron, there's no more fusion in the core.
Okay.
And when we talk about the supernova event, we're going to see that during the supernova event, we do have, it's called nucleosynthesis. We do have fusion going on, but it's like local pockets.
Okay.
But it's not in the core.
Okay.
Yep. Yep. So here's the onion. Okay. So hopefully then you kind of look in the center. You're going to see the iron. Okay. Look outside there. We see a little bit of silicon still. Then out beyond that, we talked about neon, carbon, helium, hydrogen. So that's kind of the onion. Just before it blows up. So again, just kind of showing you the onion structure. This is kind of trying to emphasize that that these are down here. This is how complicated your element could be. So these are by like the number of protons in the center of an atom, that type of element, or wait a minute, atomic mass. This is the protons plus the neutrons, basically. So iron is kind of a tipping point. What's fission? Does anybody remember what's nuclear fission? Yeah, it's breaking it apart. Yep. So fusion is what we do in the stars, and fission is what we do like with uranium. We take uranium, a big old kind of unstable atom that wants to kind of fall apart anyway, and as it falls apart, it releases energy. Okay. This is kind of a busy little slide. We talked earlier about atoms in general. So what are the two colors? What are the two particles in the nucleus of an atom? Protons and neutrons, exactly. And so the thing is, the more protons you get, then you get another element. You get a more complicated element. And what this is kind of talking about is it kind of, the way nuclear fusion works is the whole twosies thing. So a lot of times we have a lot of elements that have an even number of protons in their core, and that's not an accident. That's just kind of the way it goes. Nuclear fusion happens in stars. So the abundance of those elements in the universe is greater. From iron core to supernova. So I'm going to kind of talk you through the last seconds of a star, massive star. So let's see. We talked about, as it was a main sequence star and kind of went through those different types of nuclear fusion, it definitely increased the pressure and the temperature in the core. So it's not a stranger to gravity. So silicon fuses to form iron, okay, but iron won't fuse to release energy. So the star core is no longer pumping out energy. Do you guys remember, I'll go ahead and, well, I'll draw a picture. You tell me what I'm drawing. Starts with letter H. Okay, this is our sun. Okay, here is, that's the sun's atmosphere. This is, starts with letter G.
Gravity.
Gravity, thank you. That's gravity. And then it actually has this pressure going out just because of the energy it's creating. I'm going to try to make those arrows the same length. What do we call that? I'll tell you the second word. The second word is equilibrium. Hydrostatic. I think it's on your review sheet. Hydrostatic equilibrium. Okay, so we have gravity, and then we have the energy that's created as the sun has nuclear fusion in its core. Well, you figure at this point, that little iron core, it can't fuse to create this outward motion. Okay, so I'm going to go ahead and take this. I'm going to put X's through it. Okay, so the only thing that's going to go ahead and work on the iron core is gravity. So that thing collapses. Now, a minute ago, do you remember these are my atom A and atom B, and this is kind of the electron around atom A and atom B. And I told you that actually what's going to happen is a kind of a, so I'm showing you my electron cloud of A and electron cloud of B is no longer supporting the weight of that star. What happens is, picture atom A and atom B. What happens is the electrons, and P stands for protons. Yeah, the electrons and protons of those normal atoms actually kind of merge together to make what I call, what's N stand for? Neutron. Neutron soup. Anybody? Okay, so it's just that high pressure that the weight of the whole star, basically on the core of the star, takes its normal matter and makes neutron soup out of it. It also releases a bunch of neutrinos. Now, an object that is just made of neutrons, basically, isn't that weird? Not normal matter, because normal matter has, you guys told me, protons and neutrons and electrons. So the protons and electrons join together to make neutrons and join the neutrons that were already there. It's neutron soup. Okay, we call that, actually, there's objects, and we'll be looking at some pictures of them. There's objects out there that are called neutron stars. And that's a neutron star that's created at the heart during the heart of this object that's blowing up. Okay. So there you go. So on your, this is where, on your thing I gave you. So we got the supernova is the blowing up part. I'm not done talking about the blowing up part, okay? Supernova is the iron core, blah, blah, blah. But notice that we have a neutron star, which I'm just telling you about. But I have a little box here that says if the star, as it was a main sequence star, is greater than 25, not just 8, but 25 times the mass of our sun, then those neutrons, so we got neutron soup. The neutron soup for a neutron star holds it up from collapsing any further. But if it was more massive than 25 solar masses, guess what? It takes the neutrons and they combine into what we call a singularity, which I'm going to talk about in the next part, and that's actually a black hole. There's different types of black holes. Black holes that come from stars are called stellar black holes. Get it? Star black holes, stellar black holes. Okay? So that's kind of the way that works. So what we call neutron degeneracy collapses, or neutron degeneracy can't support the weight. So it's, and you're like, well, if it's not neutrons, what is it? It's something that has characteristics of mass and spin, but it's just, it's not normal matter. Just trust me. So, all right. So to talk about the supernova part, the blow up part, whether we end up with a little core that's a neutron star or a little core that's actually a black hole, okay? And I think did he talk about this too? So the stiffening part. So whether it's neutron degeneracy that makes a neutron star or it collapses, basically there's a stiffening part. Now we have gravity coming in, okay, and then actually as the matter coming in, it's like if you throw something at the wall, okay, it hits the wall, which is hard, and it comes back. So you have stuff coming in while stuff has hit the wall and is going out. So basically you have material going both directions, okay? And that is the explosion part of it. And I mentioned this nucleosynthesis, and so actually as you have the rebounded stuff going out and gravity making stuff, the other material didn't get the memo, they're still coming in because of gravity, okay? Those areas actually can have high enough temperatures and pressures to fuse things into heavier elements, called nuclear synthesis. There you go. What else we got? Yep, this talks about material moving towards, matches up against material moving out. All right, so let's talk guts then, right? So when we started this, we kind of showed the ring of material here and kind of the jets of material. Those were the remnants of a supernova, leftovers, remnants from a supernova called supernova remnant. Yep. So at the center of a supernova remnant, you should always find either, because supernova remnant was from a star blowing up. So that little core is either going to be a neutron star or a black hole. And hopefully we're all on the same page with regard to what mass that breaking point is. This is just a normal, this is another galaxy, but you know how we do a lot of comparisons? So this is what it looked like now. Obviously, you can see a difference between those two photos. That's just simply showing a massive star that ended its life in a supernova event. Very energetic. And I like the video where he has that, he's cheating, right, man? Even more than my go-to scope. He's got that scope that's on just a computerized scope, and so he looks at galaxies, and looks for a little blip in galaxies. So here are some other ones. So this is without the supernova event. This is in 5 different other galaxies. And this is with the supernova event. I've got a friend at the observatory who he's really into finding or looking at these after they've been published. You know, he doesn't find them. Before and after. Before and after. Before and after. Before and after. So these would be other galaxies. supernova remnant in different wavelengths. Supernova remnants. Supernova remnants. It's hard to say remnants. See, I had a lot of pictures. Supernova remnants. I thought this was interesting. So this is looking at kind of, it might even be the one we just looked at. Remember kind of the ring material? So think that in here is either the neutron star or the black hole. 1997, 2003. That's kind of neat. It's like these little nodules, they're increasing. There's kind of a delay in the glowing of that material. So this is showing you, so when it's bright, like we saw a minute ago, you know over time that energy is going to dissipate. And that's actually what's shown here. Now don't forget, like the caption says, this is actually apparent visual magnitude. Is that a lowercase m or an uppercase m? Lower, yep, apparent magnitude, very good. And is the scale right? So we have an apparent magnitude of 15 down here, and then an apparent magnitude of 5 up there. Yep, remember the lower the apparent magnitude, the brighter it is. So it's kind of showing you the decay over lots of it. So one of the last things I want to talk about is this idea of, we're going to focus on, no pun intended, neutron stars. So this is a supernova remnant. This is Messier object number 5. You know how we talked about like M13, M31. This is M1, Crab Nebula, which is a supernova remnant. And if it's a supernova remnant, I told you it's either got to have, and they're extra retired, a retired neutron star, a retired black dwarf, right? Or black dwarf, black hole. So there's an object in there that is actually sending this signal, this pulsing. And I'm going to try to kind of talk to you why this pulsing, anytime you see a pulse like this is a pulse from a neutron star. It's a neutron star in there sending this information out. They're very short blips. So this pulsing from a neutron star, it's kind of confusing. They call it a pulsar. But the pulsar is the signal coming from the neutron star. Okay, so somehow you want to connect those two. At first, when they found pulsars, they're like, oh my gosh, somebody's sending us, like aliens sending us a signal. Let's go ahead and decipher this. But no, it was not. In fact, I think the funny thing is Jocelyn Bell and her folks, they call them LGM sources, these pulsar sources, stands for Little Green Men. Anyway, nothing to do with Little Green Men. So pulsars are neutron stars. So let's see how that works. So this, I don't know if you can, this would be a neutron star. The blue orb is not a planet. The blue orb is a neutron star. Very exotic sort of thing. But doesn't this sort of kind of remind you of the Earth's magnetosphere? Me too. So kind of go with that, because it is. It's like a magnetic field. And so what happens from that magnetic field is it squirts out energy that we can pick up as a signal. So now here's where the pulsing comes from. Let's say that, let's say I'm a neutron star and I'm spinning, which most neutron stars do. And let's say I am squeezing out material like this. Okay, I'm squeezing out here, I'm squeezing out here. Now, so you guys see it? Now you see it? Now you see it? Now you see it? Okay, that's just from the rotation of the neutron star. Okay, so if you are in the field of view of this signal that's being squished out from the neutron star, that's where the pulsing comes from. Okay, there you go. It's called kind of a lighthouse model. This is just showing you the same thing. So not all neutron stars would we see as pulsars, but when we see a pulsar, it's coming from a neutron star. Cool. Well, that's it, Mom. So on Monday and Wednesday, we'll talk more about just black holes in general. Remember, stellar black holes are not the only type of black holes, but a black hole, they have things in common. So does that mean 2 parts are due for, okay, I'll put that on Twitter.